Noise cancellation. It's been around for a while, but why is it so desirable? Well, noise cancellation makes it a lot easier to enjoy loud environments. If you're driving down the road in your car, noise cancellation can cancel out some unwanted road noise, wind noise, and even engine noise. If you're flying on a long flight in an airplane, well, noise cancellation can cancel out the loud engine noise, leaving you free to enjoy movies or music. There are two types of noise cancellation, passive and active. I'll talk about both briefly, but I'll go into more depth about active noise cancellation. Passive noise cancellation uses special materials like absorbent foam or just thicker walls or windows to cancel out unwanted sound. Active noise cancellation uses a microphone, signal processing, and a speaker to cancel out unwanted sound. A microphone picks up this undesired sound, some black magic signal processing is done, and a speaker outputs a cancellation signal, leaving you with a much quieter environment. In a basic active noise cancellation system, the system picks up noise with a microphone. It then inverts this noise and outputs it to a speaker. The speaker will play the opposite of the noise signal, and ideally they should cancel. On the left you can see both the original noise signal and the inverted cancellation signal. On the right is the sum of the two signals, and you can see ideally this is zero. I say ideally, but in reality this never happens. There's always some part of the noise signal that isn't completely canceled, and you're still left with a small bit of noise. The reason the noise isn't completely canceled is phase. Not electrical phase in this case, but acoustic phase. If the cancellation signal isn't 180 degrees out of phase with the noise signal, then complete cancellation won't occur. So if you have a slight mismatch, then you're going to be left with some noise signal. This mismatch happens if the noise source moves at all with relation to the cancellation speaker. Here I have set up a signal generator generating a sine wave at 2 volts peak to peak at 1 kHz. This signal is being split to two channels on the oscilloscope. One channel represents the original noise signal. The other channel, representing the active noise cancellation signal, is inverted from this signal. These two signals go to two speakers. Here's the oscilloscope with the signal generator's output turned on. The yellow signal and the green signal are exactly 180 degrees out of phase. The red signal is the sum of the yellow and the green signals. You can see that it's virtually zero, and the scales for all three waveforms are identical. Now, this is the electrical phase of the signals, not the acoustic phase. We'll see in just a minute how the acoustic phase affects noise cancellation. Now I have two speakers set up. The speaker on the right represents the active noise cancellation speaker. The speaker on the left represents the noise source. The sine wave from the signal generator is going to both speakers, but the leads are reversed on the speaker on the right. This effectually inverts the signal on the left, so that cancellation will occur. Signal is currently going to both speakers, but some cancellation is occurring. I'll disconnect the leads so you can hear the difference. Now, only the speaker on the left is outputting sound, and the sound is much louder. Let me reconnect the leads and enable active noise cancellation. Now let me move the speaker on the right to simulate the noise source moving further away from the active noise cancellation system. Now listen what happens as I move the speaker further away. The signals coming from the two speakers look something like this. When the signals are completely out of phase, the positive peak of one signal will line up with the negative peak of the other. When you add these two, they sum to 0, so you get the nice flat 0 signal on the right. But we don't actually hear 0 when we perform this experiment. Here, you can see two signals that aren't perfectly out of phase. Now, since they aren't out of phase, there is a slight signal that results from their sum. This is shown on the right. This is why we still heard some sound during the experiment. No matter how well we spaced the two speakers, there was some slight phase misalignment, so the two signals never actually canceled. Now, as a worst case, the two signals could be in phase with one another, so that when added together, you get twice the original signal. You could hear this as the loud points as I move the speakers further away. So what happens when the noise changes frequency? Well, from this table, you can see that 1 kHz has a wavelength of around 34.3 centimeters. Now that's in standard temperature and pressure air. If you change the temperature or the pressure of the air, then the wavelength will change. 34.3 centimeters is very small compared to the length of the table I was using. If you go lower in frequency, say to 100 Hz, the wavelength is 3.4 meters. Now that's much longer. Let's see what happens then. Now I've lowered the frequency to 100 Hz. You can hear pretty good cancellation, but the distance between the two speakers is much further than the 1 kHz example. Now let me disconnect the speaker on the right so you can hear the difference. So you can hear that's quite a difference over a distance of roughly half a meter. Now let me move the speaker back and show you the difference as the distance increases. So you can hear it getting louder, but it's still nowhere near as loud as the uncancelled signal. And this is over a distance of roughly 1 meter. Now let me move the speakers closer and observe the change in the opposite direction. Silence. Now, for 5 kHz, the wavelength is only 6.9 centimeters. That's really small when you compare it to the size of the table. Here we have a 5 kHz sine wave going to both speakers. You can hear the signal fairly loud even though the speakers are touching each other. Well, let me disconnect the speaker on the right to hear it so you can see the uncancelled sound. That's it with it uncancelled. And now cancelled again. No change. Anyways, let me show you moving the speaker back just for old time's sake. You can hear a little bit of an increase. I'm trying to get a small enough increase in the distance so we can hear the minimum point, but it's very difficult. So throughout the whole range, there are very few points where the sound is much quieter than it is at any other point. There's just not good cancellation at 5 kHz. Well, what about 500 Hz? Here, we can hear a little bit of sound. So let's check out the uncancelled signal. Quite a reduction. A lot better than 5 kilohertz. So let me move the speaker back and show you the range. So it takes a much further distance than the 5 kilohertz or the 1 kilohertz. And I think we've passed the maximum, and it's getting quieter again. And then louder again. So for an average car environment, it's going to be roughly the size of the table I was using. Yeah, maybe a little bit bigger or smaller, like if you're driving a Mini Cooper or a big Escalade. But you're going to get the same general behavior. So the behavior that we observed on the tabletop experiment was that lower frequencies were much better canceled throughout a larger range of distances. The higher frequencies, they just kept fluctuating from minimum to maximum, and so you never really get a great cancellation anywhere on the table. Yeah, maybe if the noise source was right in front of the active noise canceling system, it might cancel. But it's not going to be anywhere near as canceled as a lower frequency sound. When you get into the sub 500 Hz range, you're going to get fairly good cancellation, with the cancellation getting better and better the lower you go. It's kind of like the limbo. Active noise cancellation. As Martha Stewart would say, it's a good thing.